We're going to do simpler things than we did the last couple of days. And to make it simpler, what I want to do now is find the voltage in the opposite situation where you do know the charge distribution. Then you aren't going to have to solve these partial differential equations. So let's investigate that. Now, the way to do that is to start by asking, what is the voltage produced by a single charge? If we could figure that out, then because we know we have superposition and the effect of 3 or 4 charges is just the sum of the effects of the individual ones, then if we could find the voltage due to one charge, we could just add all of them up, just do an integral. Oh boy, this looks grim. Who did you kick? Who did you kick? What happened?
Partially Achilles tear.
You what?
Partially tore my Achilles.
Oh, geez. How'd you do that? Frisbee should be safe. I mean,
Yeah, that's what I thought.
it's freaks like that. When I was in college, the captain of our ski team broke his leg climbing out of his bathtub. You know, not skiing, something respectable, but climbing out of the bathtub. Okay, so the problem we want to look at today to start out with is, what is the voltage produced by a single charge Q? It's at some distance r. Okay, now we know how to do this because we know that the voltage is the change in potential energy between the initial and final point divided by the charge. So all we really need to do is find the potential energy that it takes to move a charge from some starting position to some final position. So what we do is we go back to our definition. Vf minus Vi is 1 over Q times the work I do to move the charge from the initial position to the final position. So that is PE final minus PE initial. That was our definition. Now, we know what that is. PE final minus PE initial is the integral of Fm dot Vr, that's the work I do, and that, since my force had to be equal and opposite to the electric force, because I have to move it at constant speed, was minus F electric dot dr, but F electric is QE dot dr. And therefore, the voltage, V final minus V initial, is minus the integral of V dot dr from the initial to the final position. Okay? Now, E, due to that charge Q, is KQ over R squared R hat. So, KQ over R squared R hat dot dr. But R hat and dr are in the same direction. Dr is just an extension of the vector r, so it lies in the direction of the vector r from the initial to the final position. So we get minus KQ over R squared dr from the initial to the final position. But I know how to do that. The integral of that is just 1 over r. So it is KQ over R between the initial and the final position. So it's KQ times 1 over R final minus 1 over R initial. So now we get to choose the zero of potential to be anywhere we want it, of voltage to be anywhere we want it. For this situation, it'll be simplest if we choose the voltage to be 0 when you're infinitely far away. You can choose anything you want. But for this case, it'll be simplest if we do that. So we make V initial 0 when R initial is infinity. Well, 1 over infinity is 0, so the conclusion is that V at position R is simply KQ divided by the magnitude R. Now that's fine when we were doing a point charge like this. Would it have worked if we were considering a cylinder? Think back to the problem we did, Gauss's law, where we had a conducting cylinder. To make it work accurately, the cylinder had to be infinitely long, right? So that you always stayed far away from the ends. But if you were to make the voltage equal to 0 at infinity, and had some charge on the cylinder, you'll have a conflict at infinity along the axis and infinity out here. Because you said at infinity it should be 0, but that would mean that the voltage on the cylinder had to be 0. So it would not do to choose the voltage 0 at infinity if you wanted to consider a cylinder. Instead, you'd make the voltage 0 at some other point. So there really doesn't matter what you pick. You have to pick something sane. You have to pick something that doesn't give you conflicts. Am I just confusing, or did that make sense? I'll make it make more sense in a second. Basically, when we go back and we ask what is the voltage associated with a cylinder with a charge Q on it, you get something that looks like the log of R, like the log of R. And the log of infinity is infinite. Whereas from a sphere, the voltage came out to be 1 over R, and then that goes to 0. So you have to sometimes be careful. But as long as you're dealing with point charges, then this works fine. In fact, as long as you deal with the real world, this works fine. It's when you make these approximations that the cylinders are infinitely long and the plates are infinitely big that you could get into trouble. All right. So, armed with that, we are now able to write down the voltage due to any charge distribution. So now let's suppose we have some charge distribution here. You got charges all over this place. And let's locate the things relative to some coordinate system. And we'll let r prime be the vector that goes from the origin to where we have, in a little volume of space, a charge dq, which is rho of r prime times the volume of that little box. That will give us the charge at this point. And let's find the voltage at some position r. Okay. Now, in order to do that, the distance from the charge to where we're finding the voltage, which is the r over here, the distance from the charge to where you're finding the voltage, is r minus r prime. And therefore, what we have is that the voltage at position r is the sum of the voltages produced by each of these little chunks. So let me write the little element of voltage at R due to that little chunk of charge right here is, according to that, K times the element of charge, which is rho of R prime, d cubed R prime. That just means the volume of the little box there. That's just my way of writing the volume. Divided by R, which is the magnitude of R minus R prime. And therefore, if I want the total voltage at R, I have to add them up for all the little chunks, and that means I have to do the integral. K rho of R prime d cubed R prime over R minus R prime. And so I've now been able to write down the voltage if I know the charge distribution. Now, the seeming advantage of this would be the same when I wrote the same thing for the electric field, which we did a few days ago and you had on the first homework problem. The result we had was the electric field at point R was equal to the integral K rho of R prime R minus R prime d cubed R prime over R minus R prime cubed. Now, if you look at those two and realize that if you wanted to find the electric field from the voltage, you would take E of R is equal minus the gradient of V of R. Which is easier to do analytically, to take an integral or to take a derivative? You can always take a derivative. You struggle like mad to figure out what's the inverse of that, what's the integral. But the derivatives are easy. So it would appear that taking the gradient of V maybe is simpler than finding E from this, because V is at one integral, d cubed R prime. For E, you would have to do three integrals, one for each direction. One for the x direction, one for the y direction, one for the z direction. And so it would look as though, since one way you do three integrals, no derivatives, the other way you do one integral and one derivative, it might be easier to find V. Making sense? On the other hand, suppose that integral that you've got there can't be done analytically, the integral for V. You have to do it numerically, which would happen in most situations. How do you find the derivative if you've done a numerical integral? You have to do that integral at very close neighboring points. Subtract them. Divide. Now that's getting to be really messy, because when you want integrals very small distance apart, then you got to do the numerical integral to great accuracy, so that when you subtract, if you subtract 109.2 from 109 and you just did three figures, you'd get 0. So in practice, V done this way is only useful if you can do the integral analytically. If you can't, you're better off to just grit your teeth and do that numerical integral once for E. So although if you look at elementary textbooks, they always make a big point of find v, then take the derivative. That's great, except in practice you can't usually do it. You have to do it numerically, and then it's very bad to try and find derivatives numerically. For integrals numerically are easy, integrals analytically are hard, derivatives numerically are hard, and analytically are easy. So it's a question of whether you can do it analytically or not. Making sense to everybody? Okay, let's give an illustration of how this would work. So let's suppose we have some known charge distribution. And let's pick to see exactly how this is going to play out. Let's take a nice simple situation. In which you have a circular ring centered at the origin. And you place a charge Q on this ring, which has a radius A. Okay. Now, let's use cylindrical coordinates. That would be the obvious choice to match the symmetry here. And make this the z-axis and let it lie in the xy plane. So it lies in the xy plane. And so this angle is the angle theta. Okay? So let's find the voltage at some arbitrary point. So let's go out here and find the voltage at some arbitrary point, x, y, z. Okay? So what we need is we have to be able to stick in, we need a value for this, we need this, we need this. Okay? So R is x hat, y hat, z hat. R prime is, well, the x component. If I write this in spherical coordinates, then the coordinates of a given point there are a rho hat, and that's it, because z is 0, and so to get to this point is just a rho hat. But if I want to write it in terms of x, y, and z, so that I can readily subtract r prime from r, then the x component is rho times the cosine, but rho is a, so it's a cosine theta x hat plus a sine theta y hat. Everybody see that? Radius is a, and the x component is the cosine of that angle, the y component is the sine, and z is 0, because the charge is in that plane. Okay, so r minus r prime is equal to, in the x direction, x minus a cosine theta. In the y direction, y minus a sine theta. And in the z direction, just c. And so the magnitude, r minus r prime, is the square root of this squared plus that squared plus that squared. So you have x squared plus y squared plus c squared. That's r squared. You have a squared cos squared plus a squared sine squared. That's a squared. And then you'll have minus 2ax cos theta minus 2ay sine theta square root. Okay with everybody? All right. Now, we need the little charge in this little chunk. So what will that charge be? Well, it'll be the charge per length times the length. Right? And so this rho d cubed r prime will become, in our case, not a volume integral, because the charge is just on a ring. All we really wanted, this thing was just supposed to give us the charge in that little box. Well, that little box now is just a little length of the ring. Making sense? So this would be Q over 2 pi a times the length of the ring, a d theta. The length of our little box. And so that is Q times d theta over 2 pi. Well, of course it is, because it's the fraction of the total charge that is in the length d theta. And that's d theta over the total theta, which is 2 pi. So I now have everything I need to write down the voltage at position R, which is the voltage at X, Y, and Z. And going over to there, it'll be K times the integral from 0 to 2 pi, to go all the way around the ring, of rho, which is Q over 2 pi times d theta, Q over 2 pi times d theta, divided by this thing, r squared plus a squared minus 2ax cos theta minus 2ay sine theta to the 1/2. Okay? Now, look at this integral. They have a heart attack. I mean, you're integrating 1 over a constant, the square root of a constant, minus some constant sine theta, minus some constant cos theta. You're not going to do that analytically. So in general, you would have to do that numerically. However, there is one situation in which you could do it analytically. And that is if you wanted to find it on the axis. If you wanted to find the voltage on the axis, where x and y were equal to 0, then that would be a trivial integral. Completely trivial. Because then it's the integral of a constant, so you just get 2 pi times this stuff. So this would go if x were equal to y were equal to 0, so you were on the axis, you would get kq over 2 pi, integral from 0 to 2 pi of 1 over r squared plus a squared to the 1/2, which is simply kq over the square root of r squared plus a squared. So in that situation, doing the integral would be easy. Now you would need to take the gradient to find the electric field. Well, by symmetry, on the axis, can there be an electric field in the x or y directions? No, because any direction of x or y is the same on the axis. Make sense? So the only direction the electric field could have was the z direction. And therefore, to find the electric field, all we'd have to do is find the z component And that would mean to take the derivative of this thing with respect to z, which along the axis is r. Making sense? So E at 0, 0, z would be minus d by dz of kq of z squared plus a squared square root, because on the axis r is equal to z. And that's a trivial integral to do. You get kq, then you'll get minus a half. It cancels that minus sign, so you got a half. And you got 2z over z squared plus a squared to the 3/2. So the electric field, and that's in the z direction, the 2's will cancel out, and you get kqz over z squared plus a squared to the 3/2. However, if you were not on the axis, then you have to actually calculate all the derivatives, the x, the dv dx, dv dy, and since doing that integral analytically isn't possible, you'd do it numerically, you'd have a nightmare. So, if we're not on the axis, we'd better come down and do E. So, to do E, we already have everything we need for this integral because we've evaluated them up there. So let's write down the integral we'd have to do for E. So E at x, y, z in general will be k. Rho is what we wrote down there. Q over 2 pi integral theta equals 0 to 2 pi d theta. We need r minus r prime. Well, we've got it up there. X hat times x minus a cos theta plus y hat times y minus a sine theta plus z hat times z. And then we're supposed to divide by r minus r prime to the 3/2, which is that thing. R squared plus a squared minus 2ax cos theta minus 2ay sine theta to the 3/2. Okay, so that would mean that Ex at x, y, and z would be equal to kq over 2 pi integral theta equals 0 to 2 pi d theta x minus a cos theta over that thing to the 3/2. And that's a numerical integral, but we can do that. And once we've done it, we're done. We don't have to take a derivative. We don't have to do all sorts of numerical integrals arbitrarily close to this. Just for fun, let's write down EZ. At 0, 0, z. Problem we just did over there. So you get kq over 2 pi times z, because z is a constant with no thetas involved, times the integral from 0 to 2 pi of d theta over, now, x and y are 0, so you get r squared plus a squared to the 3/2. But that's a constant. That integral is 2 pi. So you get k q z over r is z plus a squared to the 3/2, as we got over here. Okay, the process making sense? So the bottom line is, this looks nice, but doing v this way is usually not useful unless you can do the integral analytically, which only very rarely can you do. So normally you're better off to go directly and find the electric field. Okay, now, I want to make clear what I said earlier about the cylinders, for example. Everybody's happy with this? I know better than to ask a question like that. Okay. What do I need to do to make that more clear?
I need to go back to school.
You are in school.
I don't know. It's I get lost so quick when you're talking about transforming things. I have to think for a very long time, even just to come up with, like what the length is of something in a different coordinate system.
Don't feel bad about that. That stuff is not trivial. You just have to do these a lot of times. I've been looking at this for a little bit longer than you have. And as a result, it may sound, I say it in a correct way, but that doesn't mean I understood it that way the first time I saw it. I certainly didn't. And don't get discouraged. It just takes doing it a while, and it will become apparent. But it takes a while. Nobody does this, at least nobody I ever met does it trivially the first time. How does what?
I don't even know how I'm going to do the homework then. I look at this. And
You're going to come in and talk to me.
I could just write this stuff on the page and I wouldn't know what I'm saying. And I could be completely wrong.
But that means you're going to come in and talk to me.
I will.
Okay. Anybody with specific questions on this that you already are aware you don't understand? As opposed to going home and trying to do it and discovering that you didn't understand. Yes? The R prime locates the charge that's producing the voltage or the field. The R locates where you're finding the voltage or the field. That's often the confusing thing. R prime just tells you, here's this charge. It's going to produce a field over here. The R prime says where this one is. The R says where you're finding the field. Okay? Well, now, let's go back and we did these problems with the spheres and the cylinders. Let's, instead of finding the electric field for those configurations, let's find the voltages for those configurations. So let's ask ourselves, what is the voltage given that arrangement of spheres or cylinders? So let's start with the spheres, because that one had a perfect symmetry to it. So Let's run this up. And remember our sphere problem. We had a charge Q0. Then we had a surrounding sphere with R1, R2, Q1, and another surrounding sphere with R3, R4, Q2. Okay? Now, we know that the electric field always looks as though it were due to a point charge located at the center, where the point charge is all the charge that's inside where you're looking at it. So, in this region, the electric field, let's start out here, because we are going to take the voltage to be 0 at infinity. And so, let's work from R greater than or equal to R4. Now, the total charge that's inside is Q0 plus Q1 plus Q2. So, from our conclusion up there, we know that V of R must be equal to K Q0 plus Q1 plus Q2 divided by R. Everyone understand? Because we know it's the integral of E dot dr from infinity to the point, and we know that E is exactly what it would have been if all the charge had been located at the center, and we know that when that happens, you just get KQ over R, so it must be that. Yes? Yeah, this is because it's spherical. When you do cylinders, it'll be very different.
So
Yes.
the little r denotes the radius that we're taking it at the time.
Yes, precisely. Yes.
Explain why we're taking it from infinity.
We were free to choose the 0 anywhere we wanted. Top board over there. VF minus VI in general was that thing, 1 over RF minus 1 over RI. I chose to take the voltage to be 0 when R was infinite. I can choose the 0 anywhere I want. I choose that to be the 0. For spheres. It won't work for cylinders, but for spheres, that's a nice choice. Voltage, like potential energy, is only defined as a difference. So you can take the 0 anywhere you want. Okay? Now, R3 less than R less than R4. What is the electric field in this region? 0, right? So how much work does it take to move from here to here? None, because there's no force. So the voltage will not change in going from here to here. Put it another way, the voltage on a conductor is constant. The voltage is everywhere the same on a conductor. So, in this region, V of R will be the voltage that you had reached when you got to this point. When you got to this point, and that voltage is K, Q0 plus Q1 plus Q2 divided by R4. And that voltage will stay constant until I get to the inner surface of this. Right? Everybody following that? Okay, so now R2 less than or equal to R less than or equal to R3. Well, now we have to be a little more careful. We go back to our equation up there. And V of R, so let's do it on this chunk of board. V final is V of R, minus V initial, which is V of R3, is supposed to be equal to KQ. This will be the K times the Q that's inside where I am, because that's what's determining the electric field, times 1 over R final, which is 1 over R, minus 1 over R initial, which is 1 over R3. Now, KQN, QN, the charge that's inside this point is Q0 plus Q1. So it's K, Q0 plus Q1 times 1 over R minus 1 over R3. And therefore, V of R is equal to V of R3, but V of R3 is this. And so it is K times Q0 plus Q1 plus Q2 over R4 plus K Q0 plus Q1 times 1 over R minus 1 over R3. I don't want to write that over here again, so I just call that F1. Everybody understand physically what went on here? We're talking about the work you have to do per charge to move the charge from infinity to a given point. So first, you had to do this much work to get it up to here. Then it was free to go over to here. Now you have to do that much work to get it into here to position R. Now, what happens in going from here to here? That's free, because there's no electric field there. So, in the region R1 less than R less than R2, the voltage is the voltage you had when you reached this point, which was this thing evaluated when R is equal to R2. I just put in R2 here. And so I'll just call this F1 of R2. Okay so far? And the last stretch is R less than or equal to R1. Well, now the voltage will be what will happen. I've got a certain voltage here, and now I have to go from here in. And so it will be V of R minus V of R1 will be, go K Qn, but Qn is just Q0 now, times 1 over R minus 1 over R1. And therefore, V of R is equal to V of R1 plus KQ0, 1 over R minus 1 over R1. But V of R1, that was this. So it is F1 of R2 plus KQ0, 1 over R minus 1 over R1. And we'll call that F2 of R. So what does the graph look like? If you made a graph of V versus R, starts out here at infinity, where's 0, rises like that until you reach the point R4. It is then flat, no change, until you reach the point R3. And then it rises until you reach the point R2. And then it is flat until you reach the point R1. And then it rises. So that'll be what the voltage looks like as a function of R. Make sense? Is there what? Because between R2 and R3, you have an electric field. Between R4 and R3, there's no electric field, so it's flat. Between R2 and R1, there's no electric field, so it's flat, because you don't do any work. They're conductors, they have a constant voltage. But between R3 and R2, you're moving in between the outer and the inner sphere. And then from R1 in and outside of R4. In those regions, there's electric field, so you get a voltage that changes. Yes?
So the reason why it's constant is because R value for inside the conductor.
Precisely. And inside the conductor, there's no electric field. That means it takes no work to move a charge from one place to another. And that leads to a fundamental fact, and that is not only is the electric field inside a conductor 0, but the voltage inside a conductor is constant. Not necessarily 0, but constant.
It's not just an analogy. I don't think it's useful, but if you want to relate the charge and V field and potential, you could think of the charge as how much dirt there is, potential and how high it was.
It's that. No, that's fine. That's the analogy we used last semester, contour lines. Contour lines are lines of equal potential energy if you're talking about climbing a mountain, equal voltage if you're talking about electricity. If you want to find out how much work you have to do to climb the mountain, you take the difference in contour lines and multiply by your weight. To find the amount of difference in energy, in an electric case, you take the difference in voltages and multiply by the charge. Okay. Making sense to everybody? Now, if we had done this problem for cylinders, here would have been our situation. V final minus V initial would have been 1 over Q minus sine integral E dot dr from initial to final. But what did the electric fields look like for cylinders? Were they 1 over r squared? No, they were 1 over r, right? And so you got minus 1 over q times some constant divided by r. And what's the integral of 1 over r? It's log, right? Log r evaluated between initial and final. So now, if you took the initial position to be at r equal infinity, you'd have had the log of infinity, which is infinite. You couldn't very well make that 0. And so if we were doing cylinders, we couldn't make the choice. The voltage is 0 at infinity. That's mathematically. Physically it is. Then now you'd have 2 conflicting conditions. If you go infinite along the cylinder axis, you've got the voltage on the cylinder. If you go infinite that way, you were supposed to be getting 0. You'd have 0 equals 7. There'd be an inconsistency. And that's why this all arises by making the approximation the cylinder is infinitely long. If you don't make that approximation, you'll be fine. But of course, you also can't solve the problem. Okay? All right. Now, the next thing we're going to do, we'll do 2 things next. We're going to, 1, ask for the total energy it takes to assemble a collection of charges, to create a given charge distribution. And then we're going to get back to what we should have been doing in the first place. Namely, all of this stuff was a convenient way to find forces. And the whole idea was you're trying to avoid this problem of having to add up infinite numbers of Coulomb's laws. So we have to now ask ourselves, okay, we found E. How do we find the force once we've got E? So those are the next couple of things we're going to do. Okay, yes? Okay, if your voltages are not very useful,